Alright, so let's start our discussion about curvature by talking about curvature of curves. In this video, we're gonna discuss plane curves, and in the next video, we're gonna talk about space curves. Then after that, we're gonna talk about curvature of surfaces and then high dimension. We'll discuss two ways of thinking about curvature of a plane curve. One is in terms of the acceleration vector, and another is in terms of the oscillating circle. So let's start with the setup. Let gamma be a plane curve with unit speed. Now observe that intuitively, the curvature measures how fast the curves change direction. In other words, it measures how fast the velocity vector turns, right? The more that the velocity vector turns, the more curved gamma is. For example, for a straight line, the velocity keeps the same direction throughout. So it makes sense then to define the curvature as a vector to be equal to the second derivative of gamma. Or we could also say as a vector, the curvature is just the acceleration vector of gamma. In practice though, when we say curvature, we often mean as a scalar. So this could mean, if we just merely say curvature, this would mean the magnitude of this curvature vector. So then that is just the magnitude of the acceleration. However, if someone says sine curvature with respect to a given unit normal, then that would mean plus or minus of this scalar curvature. Where the sign is positive if and only if this curvature vector is in the same direction as this unit normal vector. Putting it another way, the sine curvature is just going to be this coefficient. It is just this sine curvature is just the scalar projection of this curvature vector in the direction of a given unit normal vector. But one thing is not quite clear here. Why is the curvature vector, or equivalently, this acceleration vector, in the span of the unit normal vector? So let us prove this. Let us show that the acceleration vector must be orthogonal to the velocity vector. Alright, so where does this come from? Well, we have only one assumption on the curve gamma. So let's use this. Let's differentiate this inner product, which is just 1. Right, so this is 0. Now, by the product rule, we get that this left-hand side is just 2 times the inner product of the acceleration vector with the velocity vector. So they must be orthogonal. And thus, in particular, the curvature vector must lie in the span of any unit normal vector of choice. Recall that a unit normal vector would just be any unit vector orthogonal to the velocity vector. Though usually the convention is to pick the vector obtained by rotating the unit tangent vector 90 degrees counterclockwise. Now this coefficient is then called the sine curvature of the curve gamma. So that is how we can define the curvature of gamma in terms of its acceleration vector. Now we want to describe the curvature of gamma in terms of oscillating circle. So let us first explain what's an oscillating circle to the curve gamma at some point P. It's like a circular version of tangent line, so it would be the circle that best approximate this curve gamma at the point P. More rigorously, if we pick any point Q on gamma, then there is a unique circle going through P and Q and tangent to gamma at P. And as Q comes closer and closer to P, this circle looks more and more like gamma around the point P. It becomes a better approximation around the point P. So the limit of this circle as Q approaches P, that's called the oscillating circle of gamma at P. It turns out that if this oscillating circle at the point P here, corresponding to time t, is Ct, then the curvature of gamma at this point P is just going to be equal to the curvature of the oscillating circle, which is just going to be equal to 1 over its radius. Thus another way we could have defined curvature of plane curve is by first define curvature of circles And that should be inversely proportional to the radius, because the bigger the radius of a circle, the more flat it is. Then, after having defined curvature of circles, now for every C2 curve, so every second differentiable curve gamma, we can define the curvature of gamma at a point P to just be the curvature of the oscillating circle at the point P. We could have started with that as the definition and then deduced that the curvature, the value of the curvature, is just going to be equal to the value of the acceleration of the curve at t. Alright, so that's curvature of plane curves. Next we want to talk about curvature of space curves.